Good morning. Now that we have a better understanding of what the heck a limit is, we can now use that concept to tie together the idea of differentiability. And differentiability is basically knowing when the derivative, aka that definition of the derivative limit, exists. So that limit, we can tie that together to the idea of continuity. So you've learned in pre-calc that a function is continuous if you can draw it without lifting your pencil. Well, if you think about it, that's not super mathematical. And we're going to be able to formalize what we mean by being continuous using the idea of limits. And then we're going to be able to tie those two concepts together. So first things first. F of x is differentiable at x equals a if the limit as h approaches 0 of f of a plus h minus f of a over h exists. So I actually mentioned this a long time ago. If you go back to that lecture where we talked about derivatives at a point, I brought this idea up, this idea of differentiability, and I said we'd have a full lecture on it. That would be this lecture. From the last lecture when we studied limits, we realized, well, wait a minute, limits don't always exist. So if this limit exists, and what that means is that we get a real number out of that, then f of x is differentiable there. So as an example, f of x equals x squared is differentiable at x equals 2. Because we know that if we compute this limit out, we'll get 2x, and 2 times 2 is 4. So that works. X equals 0 is differentiable. In that case, you get 0 out. In fact, f of x equals x squared is differentiable everywhere. And we can see that visually because in any case, we'll be able to come up with some sort of tangent line and be able to compute that guy's slope. So what would be an example of something that's not differentiable? Well, get rid of this. Here's a little bit more room. So what about f of x at, f of x equals the absolute value of x at x equals 0. What about this guy? Well, this is an example that I brought up again in that lecture a while back, and I said that this guy's not differentiable at the corner. And my intuitive understanding of that is because good luck trying to draw a single tangent line so that you can get its slope. Can't do it since it's a corner. Well, we now have the machinery to be able to prove to ourselves that it's not differentiable at that corner. So how do we do that? Well, we need to compute this limit and convince ourselves that the limit does not exist. So let's do that. So the limit as h goes to 0 of f of a plus h minus f of a, where a is equal to 0, over h is the same thing as the limit as h goes to 0 of f of h minus f of 0 over h. Well, f of h is just the absolute value of h. F of 0 is just 0 because the absolute value of 0 is 0. And we're going to divide that guy by h. So how can we compute this limit? Well, it's a little bit tricky because the absolute value function is actually a piecewise defined function. Right? If h happens to be coming from the right side, the absolute value does nothing to the h. If h comes from the left side, then we're going to spit out the opposite of what we put in. If you put in a -2, the absolute value of that is the opposite of -2. Since this guy behaves differently from the left and the right, I think we're going to use our left-hand and right-hand limits and compare those two. So let's do that. If we approach from the right, well, The absolute value does nothing because we're putting in positive numbers. So we get back out what we started. And h over h is just 1, so that limit is 1. Okay, let's put in values from the left. We have the limit as h approaches 0 from the left. Absolute value of h over h. Well, what is the absolute value of h if h happens to be a negative number? Let's play around with this a little bit. So let's say I want the absolute value of -3, the absolute value of -2. Well, you guys, I'm sure you all know that that's 3, that's 2, but I want to get some sort of formula. And if you think about it, 3, how do we get that? We took the opposite of the h that we put in there. That's what 3 is. To get the 2, we took the opposite of this guy. So this guy here and this guy here, that's my h. So when I come in from the left, the absolute value of h is just negative h. You might need to think about that. I've taught this course many times. This tricks people up a little bit, so feel free to pause the video and think about that. Make sure that you're convinced about that or ask about it in the discussion. Going forward, this ratio is just -1, so this limit is -1. Okay, here's a case where the left hand and the right hand limits don't equal each other. 1 is not the same as -1, so the limit does not exist. Well, since the limit does not exist, what's the answer to the question? Is f of x equal to the absolute value of x? Is that guy differentiable at 0? Well, that limit does not exist, so the answer is that it's not differentiable at x equals 0. Okay, so let's talk about where things are not differentiable. This isn't an exhaustive list. You can create kooky functions and make them not differentiable, but I think it's good to have a good graphical understanding of things that you'll probably encounter. So, not differentiable at corners. Not differentiable at vertical tangents. So what do I mean by that? Well, you could have a function. That is approaching being vertical, right? It's approaching being vertical, but it's never going to be exactly vertical because otherwise you would fail the vertical line test. We wouldn't even have a function. This guy, since it's approaching vertical, the slope of that tangent line is not defined. It's a vertical line. Therefore, since the slope is not defined, that means that this limit doesn't exist because this limit is giving us a slope. So that's a second thing to look for. And a third is if it's not continuous. So we're going to define continuous formally, but for now you can just think of it again as places with holes in your graph. Okay, so these are the three visual ones, but you can always convince yourself, or you may be asked to convince me if something is differentiable or not, using the limit definition of the derivative. So that's this guy, the limit definition of the derivative. All right, let's now talk about what it actually means to be continuous. In a formal manner. Let's actually define continuous. Again, up until now, you've thought about it in terms of not having to lift your pencil up. But let's think about this in terms of limits. So a function is continuous at a point x equals a if the limit as x approaches a of f of x equals, Well, let's see. Let's draw something that's continuous. Again, from our thinking about it from pre-calc. From my picture, as I move in from both sides, move in this way, I can compute the limit. Well, for that to be continuous, somebody has to be home here, and that thing that has to be home has to actually equal the limit. The thing that I'm getting closer and closer to is the point that's actually there. So in other words, the limit as x approaches a from either side, we have to get closer and closer to f of a. That is the definition of being continuous. So as another example of something that's not continuous, again from a pre-calc understanding, that guy's not continuous. Well, this fits into this definition because the limit, sorry, I feel like I should have, this is not a good notation. I wrote f of x here, should have written f of x here. It would have been more proper to write f of a there. Okay. So in this case, f of a doesn't even exist, right? There's no, in fact, let me try one more time. Let me not call that f of a because in this case it's not even existing. Let me just call that 3. So this is just some number up here. So before f of a happened to equal 3. So in this case, as we're approaching a from either side, f of a doesn't even exist. Nobody's home. So this isn't true, and this guy is not continuous. As another example, let me put dot up here. So let's say this is 5. So again, by your pre-calc understanding, this guy is not continuous at that point. And it's also not continuous by the formal definition because f of a happens to be 5 now. But the limit as we approach a of our function is 3. So my point is that this definition is a mathematical way of describing you don't have to lift your pencil up. That's the upshot of that. All right, so now that we know what it means to be continuous, now that we know what it means to be differentiable, I'd like to see how those two are related. So think about it. If you're a scientist, let's say you're an alien scientist, you come to Earth, you see this thing in this field, and it's mooing. Okay, you're calling it a cow. So you know that thing's a cow. And you've also studied mammals. You've discovered this large group of animals called mammals. And you realize that because of certain characteristics that a cow has, it's an example of a mammal. Because of that, the way you study the cow is going to be much more efficient because you already know certain characteristics that it has. So if it's a cow, then it's a mammal, so all the mammal rules apply. Now, if it's a mammal, it's not necessarily a cow, so unfortunately you don't get that bidirectional relationship. But at least you have some additional information. So let's think of these guys as creatures, a function being differentiable at a point and a function being continuous there. Can we draw any relationship conclusion? And it turns out we can. So it turns out that if f of x is differentiable at x equals a, then f of x is continuous at x equals a. Differentiability implies continuity. So if we were to draw two circles, I'm going to invite you to pause the video. One of those circles is continuous at A. One of those circles is differentiable at A. Based on what I wrote here, see if you can put the correct thing in the correct place. Right, hopefully you paused the video and you said, well, let's see. If it's differentiable, then it's continuous. Yeah, if it's differentiable, then it lives in the world of continuous functions. Pause the video again and see if you can put a function that lives here. So somewhere in the outer ring. Well, hopefully you said, oh, the absolute value at the corner. That's an example of a function that is continuous but not differentiable at a particular point. By drawing this picture, we also see that if a function is not continuous, at x equals a, it's not differentiable there. It's not differentiable at x equals a. If it's not continuous, then it's not differentiable. We can see that by our picture. Okay, so this is a statement that I'm telling you, it's actually a theorem. It's something that we need to prove. So why is that true? Buckle up. This is going to be the most abstract proof of the quarter. You may need to watch it a couple of times, but it's definitely worth going through. Okay, so we're assuming that f of x is differentiable at x equals a. So that tells me that this thing, the limit as h goes to 0 of f of a plus h minus f of a over h, this thing exists. Okay, it turns out that there's another form for the definition of the derivative, and that particular form is going to be helpful for what we're trying to do here. So what is this other form? I'm going to make a variable substitution to rewrite this in terms of x's, where x is defined as a plus h. Well, if we do that, let's see. If h goes to 0, then I guess x is getting closer and closer to a. Right? If h goes to 0, x is getting closer and closer to a. So let me rewrite this in terms of my x. This is f of x. F of a is still f of a. And if x is a plus h, that tells me that x minus a is h. Just subtract a from both sides. So we get this. This is another way of expressing the derivative. And hopefully it makes sense because we're literally saying, here's my fixed a, x is getting closer and closer to a, and I'm literally just taking the change in y over the change in x. Okay, so it's another way of expressing it. So we're gonna need that. This thing exists. This thing is a number. So what am I trying to prove here? I'm trying to prove that it's continuous at a. So let's keep the end goal in mind. I want to show you that the limit as x approaches a of f of x equals f of a. And you won't be able to see the pieces, but at the very least, we now have an x approaches a somewhere in here, and we're looking to prove something about that. So how am I going to do this? Well, let's start with the limit as x approaches a of f of x minus f of a. So why am I interested in that? You'll see in just a couple of minutes. So you can't see the end goal just yet. Just try to follow the logic. Well, first off, we know that the limit of a sum is the sum of the limits. This guy's just a constant. So we have this is equal to the limit as x approaches a of f of x minus the limit as x approaches a of f of a. Now again, f of a is a constant, so we have the limit as x approaches a of f of x minus f of a. Okay, so we know that that's true. But I want to explore this in a slightly different manner. This is also equal to the limit as x approaches a of x minus a times f of x minus f of a over x minus a. So why I did that, I'll explain in a minute, but do you believe that that's true? I mean, what did I do? I really just multiplied this thing by 1 because x minus a over x minus a is 1. Now, why did I do that? Well, because now I have this creature, which is this guy over here. And we know that that guy's limit exists. Well, the limit of a product is the product of the limits as long as both those limits exist. We know this guy exists, and let's see what happens with the left term. So we multiply this out. This guy is just some number. Well, what's the limit as x approaches a of x minus a? Pause the video and give that a shot. Well, hopefully you said that x is approaching a. Well, if this guy's getting closer and closer to a and I'm subtracting a from it, then that difference is getting closer and closer to 0. 0 times any number is 0. Well, let's back up here. Let's tie these two pieces together. So I guess we have that the limit as x approaches a of f of x minus f of a is 0. Then the limit as x approaches a of f of x is f of a, just by adding the f of a to both sides. Are we done? We are done. We have just proven that f of x is continuous at x equals a. So that should be mind-blowing. It should be mind-blowing because this is telling me that I don't care what your function is. E to the x, sine of x, e to the x plus sine of the x, whatever the heck you want. If it's differentiable, that implies it's continuous. We are making this broad statement about an infinite number of functions by using this abstraction and this proof. So you might need to sit with this proof, re-examine it. I do think it's worthwhile. It ties together a bunch of limit properties, definition of the derivative, definition of continuity. A lot of goodies are in there. All right, so as a final example, let's do one more example with differentiability and continuity. So example is the function f of x equals x times sine of 1 over x plus x. X is not equal to 0. 0 of x equals 0. Is this guy continuous? Is it differentiable? So here's kind of a kooky looking function. If you put it into your calculator, you'll see it behaves pretty crazily. And that's because of the periodic nature of the sine function. Piecewise defined, it's a bizarre function. So we want to find if it's continuous and whether it is differentiable. Well, I'm going to do the continuous first because if it's not continuous, that means it's not differentiable. Remember those two inner circles. If it's not continuous, it's not differentiable, and I don't have to do any work for the differentiable piece. If it is continuous, then I'll have to check out the differentiable piece. So continuous. The limit as, let's see, x approaches 0. And I need to be clear here. I'm talking about, my question is this guy continuous? Is it differentiable at x equals 0? That's what I'm interested in. So for the continuous part, let me take the limit as x approaches 0 of my function. Well, if I'm approaching 0, then x is not equal to 0, and we have x times sine of 1 over x plus x. So is that limit, is that equal to 0? Because that's what f of 0 is. Well, as x approaches 0, this guy gets close to 0. This guy gets close to 0. And sine of 1 over x, it's bopping back and forth forever and ever between -1 and 1. Any number you put into the sine function, as long as we're not dividing by 0, which we're not because x is approaching 0, is going to be bound between -1 and 1. So I'm multiplying something that's getting closer to 0 times something that's between here. And if you think about it, that product will get closer and closer to 0. Getting closer and closer to 0 plus getting closer and closer to 0. Yes, it is. So unfortunately, it's continuous at 0. So why is that unfortunate? Because that tells me that I need to actually check out the differentiability using the definition of the derivative. Okay, let's take a look at that. So is it differentiable? We need to compute the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. Well, that first guy is f of h, and h is not 0, so I'm going to plug h into this piece. So we have the limit, h goes to 0, of h times sine of 1 over h plus h, that's this guy, minus f of 0, well that's just 0. And we're going to divide that by h. This is the limit as h goes to 0 of h times sine of 1 over h plus 1, and just pull the h out. And then I can cancel these h's because h is not 0. So I need to check this guy's limit out. Well, the 1 is just not doing anything. It has nothing to do with h, so I'm not worried about it. So I want to know, what does sine of 1 over h do as h approaches 0? The limit as h approaches 0 of sine of 1 over h. Well, if h is approaching 0, let me just think about this from the right-hand side. Let me just plug in positive values. I'm plugging in smaller and smaller positive values in for h, and I'm taking 1 over that, which is getting larger and larger. So I'm taking sine of larger and larger numbers. Well, the sine function is just doing this as I go off into infinity in the h-axis. Therefore, sine of this thing is infinite and doesn't exist. Right? You keep plugging numbers closer and closer to 0. You're taking sine of larger and larger numbers. It's keep bopping back and forth between -1 and 1. It doesn't settle down to anything. So this is, sorry, should not have written infinity. It does not exist. But it's not infinite. Let me say that one more time. Let me actually draw the picture. So the sine function is going to do this as my axis zips off to infinity. So it's never settling down to anything. So this limit is not infinite, but it also does not exist because it's not a finite number. All right, so this limit doesn't exist. So I guess this doesn't exist. So this doesn't exist. Therefore, since that doesn't exist, I guess f of x is not differentiable at x equals 0. All right, so this is definitely a pretty heavy lecture. I would recommend watching it a second time if you can stand it. I think it will help solidify some of the concepts. Big picture, what did we learn today? We learned that functions are not differentiable when the limit definition does not actually give us a limit. Visually, if we have a vertical tangent line, if we have a corner, or if a function is not continuous, that tells us that the function is not differentiable. We formalize the definition of what it means to be continuous using a limit. We realized or proved that if a function is differentiable, then it is continuous. So a lot of goodies in there to think about. Hope that you enjoyed this lecture, and I want to say thanks for listening, and I will see you all next time.